All right, welcome to the lecture covering the 3.5 material transformations of functions. So before we jump in, I just want to kind of give you an idea of what to expect. We had what your textbook called the toolkit functions. So these were those, I think it was either 8 or 9 basic functions that you should just know. And by the end of this test, you will know them, and they're going to come up again and again throughout the semester. And actually, I've decided on my own to gather up, because they take the toolkit functions and they talk a little bit about them in section 3.2, and then a little bit more about them in section 3.3, and then even 3.4. I'm going to gather together just the information on the toolkit functions themselves and put them into a document for you so that you can have the information about the shape and the x of x table, the information about the domain of it, and the behavior of the graph all in one place instead of having to go into 3 different sections to piecemeal it together. So I'll be working on that probably later today, and I haven't decided if I'm going to do a lecture on it or just create a document, probably just a document with the time constraints that I have right now. So let's go ahead and look. What this section does is it takes those toolkit functions and it says, okay, if you know the basic shape of this of all these functions, the way you can transform these functions, which different transformations, maybe you're shifting it left or right or up and down, or maybe you're stretching it or compressing it, but it's basically the same shape, either mutated a little bit and moved around or just moved around. That's what a transformation is. So let's go ahead and dive in. Okay, so your textbook brings up this example of a Carnival Funhouse mirror. If you're familiar with those, where they're wavy looking, and when you go and you stand in front of them, it's you, and anybody else that knows you could look at your reflection and know it was you, but it's distorted. That's the same thing that we're talking about here, but except with a mirror reflecting an image of you, we're talking about some toolkit function being transformed in some way. So hopefully that visual of the Carnival House Fun Mirror makes this idea of what the heck is a transformation to begin with a little more easy to process, a little easier to process. Okay, so graphing functions. The first transformation that we get to is shifting. In other words, nothing changes about the shape, but the shape just starts moving around in the plane. And you can look at the bottom there. That is the cube root function in blue. So the general toolkit, or what I refer to as the parent function, where nothing crazy's been done to it. This blue function down at the bottom, let me get my pens going here. And I'm sorry if you can hear all those beeps and whistles happening on my computer. One of my friends won't leave me alone with Facebook Messenger. Okay, so this blue function right here is f of x equals the cube root of x. And the orange dotted function is what happened when you added 1 on the outside of the cube root of x function. So this orange function, or we'll call this g of x to have it something different, is the cube root of x plus 1. So you can see that the shape is exactly the same. The only thing that's happened is this function has moved up 1 unit. This is considered a vertical shift. Anytime you move up or down, that's a vertical shift. Anytime you move left or right, that's a horizontal shift. And let me point this out to you. Anytime you have a vertical shift happening, so this is for a vertical shift, you will see the value that you're shifting added or subtracted outside of the function. Here's what I mean by that. In this case, the function is the cube root. So you see the variables living up under the cube root, so it's a cube root function. Outside of that cube root, I've added 1. Since adding is positive, it shifted this thing up. If I had subtracted 1, let me come here. If I had subtracted 1 from the function on the outside of it, it would have shifted everything down 1. And my function would look something like this coming through. Same exact function. Well, minus the human error all over that drawing, but same exact function, this time just shifted down instead of up, or downwards instead of upwards. And that's what that gray box out to the right says. It says, you know, if the value on the outside is being added, it's going to go up, and if it's being subtracted, it is going to move downward. And Cyprian, as usual, feel free to ask any questions that come up at any time. You don't have to wait for me to stop and ask, do you have any questions? And I see you're typing something. Okay, all right. Okay, so let's look at this example here. To regulate temperature in a green building, airflow vents near the roof open and close throughout the day. The figure below shows the area of open vents. Okay, so let me just color code this for us. The area of open vents V in square feet, so that's this axis right here. Throughout the day, after midnight, in hours after midnight T. So that's what this axis is right here, purple. That's time, and the vertical axis is V, which is open vents in square feet. So I guess they measured the opening of the vent, and this is how many square feet are open this many hours after midnight. So you can see, if we're talking after midnight, the vents start opening up at, it looks like 8 o'clock. And it looks like by 9 o'clock, they're all open, and they all stay open until, oh, I have to do subtraction to figure this out. That's about 8 to 16, 17, 18. It's about 19 minus 12. So they start shutting at 5 o'clock p.m. I can't ever do time like that in my head very quickly. I always have to do the subtraction to figure out what time of day it is if it's past 12 o'clock. All right, so during the summer, the facilities manager decides to try to better regulate temperature by increasing, okay, so this is key here, increasing the amount of open vents. That means my function output V is increasing by 20 square feet throughout the day and night. In other words, all of my V values need to increase by 20 square feet. So let me show you what that looks like. We have square feet, let me color code this. We have square feet of vents as a function of time of day. And what we want to do, and so this is when I put these together, this is an output value. This is a Y value when I put those together. So what I want to do is, with that output, which is the square footage of ventilation, I want to have at any given time 20 more square feet. So what this is going to do is shift everything up 20 units. Let me make a chart to show you how to do this graphically. So this is as a function of time of day, and what we get out is ventilation in square feet. What you do when you're given a graph and they ask you to sketch the graph of the new function, you choose a few key points. So these are key points from your graph. All right, so I'm going to choose 0, 0, 8, 0. This looks like it's about 9, maybe 10. We'll say that's 9. And the output, it looks like it's about 220. This looks like it's about 17, 220. So 9, 220, and we'll call this 17, 220. And then I have this other one. Oh, that's a key point there. Let's see, that's about 19, 0, and 24, 0. Okay. So I need to make a couple more spaces for my key points. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so we have the key points: 0, 0, 0, 8, 9, 220, 17, no, 19, this is 19, sorry, 19, 220, I mean, no, I'm sorry, 17, 220, 19, 0, goodness. I've been up since 3:30 this morning working. That's my excuse, at least. I had to get these notes ready for this lecture. Yeah, I'll probably take a nap later. All right, 17, 220, 19, 0, and then 24, 0. There are key points that we have. Okay, so since this is outside of the function, this is outside of the actual function here, this is happening on the output values. So when I go to create a chart for my new function, v of t plus 20, nothing happens to my input values. They remain the same. So let's see, 1, 2, 3, 4, 5. I've got 0. Oh, goodness. I see another mistake. Not 0, 8. 8, 0. 8, 0. So 0, 8, 9, 17, 19, 24. What this says now that we've made this adjustment for the summer, at these same times, I'm going to have my original output values plus 20 to have new output values. So my new output values are 20, 20, 240, 240, 20, and 20. I'm going to go ahead and graph. So here's my new point, 0, 20, 8, 20, 9, oops, let me take these off here so we can see. 9, 240, 17, 240, 19, 20, let me take those points off as well. 19, 220, not 220, 19, 20, and 24, 20. Here's my new graph. Same shape as the last, just shifted up 20 units. All right, Cyprian, that's what I have for you on this problem. Graphing a translation is what we call when we shift something. Thank you for the green check, Cyprian. Graphing a translation is the technical word for shifting, translating it. So whenever you translate a function, all you have to do is start with a set of key points, and then you have to figure out, okay, am I shifting in my input or in my output? And whenever it's outside the function, that's your output. And then you do that in your chart and plot your new points and graph your new graph. Okay, so the same thing can be done with a table of values, and we know that this is true because they're the same exact thing. They're just different representations of the same thing. So we don't have to have a graph. We could just have a table of values or a set of points, and we could do a translation using that. Okay, so here we're given that we have our main function f of x, our new function g of x shifts down 3. So that is on the outside of your function, so that is a vertical shift that happens in your output values. So since I've already got a table of values here, all I need to know is, okay, well, what is f of x minus 3? I just subtract 3 from all of my f of x values. So here we have 1 minus 3, which is negative 2, 3 minus 3, which is 0, 7 minus 3, which is 4, and 11 minus 3, which is 8. So our new point that we come up with, we have the point 2, negative 2, because it's the same x or the same input values. The only thing that's changed are the outputs. We have the point 4, 0. Oops. 6, 4. And 8, 8. And there's your new points that you could then go graph. All right, this next one, the function h of t is equal to negative 4/9 t squared plus 30t, and this gives the height h of a ball in meters thrown upward from the ground after t seconds. So this is height after time. Suppose the ball was instead thrown from the top of a 10-meter building. Relate this new height function, b of t, to h of t. Then find a formula. Well, if you think about it, I could actually rewrite h of t as negative 4.9 t squared plus 30t plus 0. The reason I say I could rewrite it using a plus 0 is because, remember, my output is height. Well, if this first formula is representing a ball thrown upward from the ground, that plus 0 is ground level. So, to transform this function into b of t, which says we're not starting at ground level. We have the same thing here happening with the function. The ball's going to move the same way whether you throw it from the ground or not. However, your starting point's going to be different. In this case, with b of t, we start 10 meters off the ground. So there's your formula for if you're 10 meters or on top of a 10-meter building when you throw the ball. You good, Cyprian, so far? Okay. Horizontal shifts. So let's take a look at this picture here. So we're still shifting. And whenever you think shifting, which is also known as translation, and I'm going to write this down. So shifting, which is also known as translation. When you're shifting vertically, you're going to add or subtract outside the function. This is you can think outside output, and the output is the vertical variable. If you are adding or subtracting inside, Lord, I misspelled that pretty badly there. Okay, so horizontal is going to add or subtract inside. Okay, so here's one thing you have to remember. Inside, inverse. Okay, here's what I mean. Take a look at this picture here, this graph. The blue graph is the toolbox function. It's just f of x, and it happens to be a cubic. Again, notice on the inside for the orange function that I added 1. I added 1. And this shifted 1 unit, however it went left, which is in the negative direction. Intuitively, you would think that you needed to subtract that value for it to move left, but you don't. You do the inverse when you're on the inside. So if I add 1 to the input value on the inside of the function, which is the x, then I'm actually going to move everything left 1, and this happens on the x value. So this is the input. So and actually let me restate this inside inverse. I'm going to rewrite that as inside input inverse. because it's happening on the x value when you're horizontally shifting. Okay, so a general note, horizontal shift. So we have x minus h. Notice it's happening on the inside of the function. So in this case, before you actually take the cube root, you're shifting the input. H is a constant, is a horizontal shift of the function. If h is positive, okay, let me, oh, I can't believe they stated it like this. Okay, so notice that minus is in the form here. So when you see f of x plus h, you have to know that that came from f of x. Minus is in the form, so that's negative h. That's why it's the inverse of what you actually see happening, because minus is in the form. So you would think if you did x plus h, you'd go right, but that's really x minus negative h, and the negative h is what makes you go left. That's what this sentence right here is saying. So let's return to the airflow example here. Suppose that in the autumn, the facilities manager decides that the original venting plan starts too late. So notice they're talking about the input value time now. It starts too late, so they want to shift it earlier. They want to begin the entire venting program 2 hours earlier. So we have venting as a function of time, and they want to shift that time 2 hours earlier. That is 2 hours in the negative direction. So this has to become V of t. Don't forget, minus is in the form, but I want to shift it in the negative direction 2 hours. I want it to go earlier, 2 hours. So there's my new function. My new function is V of t plus 2. So if you think about it as inside input inverse, you're going to see, if somebody writes out the function for you, it's going to look like this. So since it's adding on the inside, which would normally make you think of going in the positive direction right, you have to think the inverse. So it's going left. So you actually subtract 2 from all of your input values. So your input gets shifted left 2 values. So let me go back here and grab a picture of the input-output table we already have for this function. So this is what we started with, our key points. Oops, I hit forward one too many. Okay. Let me put it here. So what we're actually going to end up doing, and I stretched it for a reason, we're going to end up subtracting 2 from each of our input values, even though it says plus 2 on the inside. So our new input values become -2, 6, 7, 15, 17, and 22. So I have the point -2, 0 right here. which is really 10 o'clock the night before. And I have the point 6, 0, right there. 7, yes, 7, 2:20, about right here. 15, 2:20, about right here. 17, 0, about right here. And 22, 0. So here's my new function. Same shape, shifted left 2 values. All right. Cool so far, Cyprian? So we've covered vertical and horizontal shifting. And the horizontal is a little tricky because you got to remember inside, input, inverse. I don't see her typing the question, so I'm going to go ahead and go forward. Okay, cool. Thanks, Cyprian. All right, so we can do the same thing in a table just like we did with vertical shifting, except now it's happening on the x value instead of the f of x value. So notice here we have minus showing up just in the position of h is a 3. So we're actually going to be adding 3 because it's inside inverse and it's subtracting it, so we actually want to add it. We're going to add 3 to each of our x values. And that gives us 5, 7, 6, 9, and 11. So I now have the points 5, 1, 7, 3, 9, 7, and 11, 11. All right, so that's it. Okay, so shifting with the graph here, horizontally, this figure represents a transformation of the toolkit function x squared. This is the quadratic that graphs as a parabola. Relate this new function g of x to f of x. So how has this changed from f of x equals x squared? Well, we need to see what f of x equals x squared looks like to begin with. So that's what I'm going to do is show you that. F of x equals x squared. Let's take a few key points, and these are just this is from your toolkit. So we have -2, -1, 0, 1, and 2. -2 squared is 4. -1 squared is 1, 0 squared 0, 1 squared 1, 2 squared 4. So we would have the point, let's see, -2, 4 is about right here. -1, 1, 0, 0, 1, 1, 2, 4. Okay, so this was our toolkit function. And basically they're asking how have you changed from that toolkit function with this new blue function here. And you can notice the shape is the same. Nothing crazy has happened. The only thing that's happened is we've shifted horizontally to the right 2 spaces. You can see each of our points shifted right 2 spaces, each of our key points. So since we shifted right, that's a positive value, but subtraction is in the form, inside inverse. So we started off with f of x equals x squared, so g of x had to be x minus 2 squared, because I shifted horizontally, which is inside the function, on the input value, I went right to, so I actually write -2 because it's the inverse. All right, and C here, and I think this might be, oh no, this isn't the last thing we have for translation. I think we've got a couple graphs to look at, or one graph to look at after this. The function g of m gives the number of gallons of gas required to drive m miles. Interpret g of m plus 10. Okay, so g of m plus 10, this is happening on the output value. Outside the function, output. So my output value in this particular function, g of m, this is the number of gallons of gas required to drive m miles. So what this says is the number of gallons of gas required to drive m miles increased by 10. In other words, that says you have to have 10 more gallons of gas to drive the same amount of miles. So for example, that might be the difference in driving, oh, I don't know, a big rig truck and a Honda Accord or whatever. You'd have to have 10 more gallons of gas to drive that same amount of miles. Now, on the contrary, if we look at g of m plus 10, notice the plus 10 is on the input variable. So what this says is the amount of miles, I started to write gallons, the amount of miles that you can drive on a certain amount of gas is increased by 10 miles. In other words, maybe you bought a compact car and now you're getting 10 more miles than you would have with the same amount of gas from your other car. So it's the difference in changing the gallons of gas and the actual miles if you're dealing with the output or the input. Okay, so now taking information from its beginning stage with a toolbox function, creating a new input-output table with its transformed function, and graphing them on the same set of axes, talking about what kind of shift and how many units it shifted. Okay, so I will do our toolbox function in purple. So we have our toolbox function, f of x equals the square root of x. So here's our general f of x table for that. I want to choose perfect squares to take the square root of. So 0, 1, 4, 9, and 16 are my input values. The square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And square root of 16 is 4. I'm going to go ahead and put this onto the graph. So I have 0, 0. Let's see, these are counting by 2s. It looks like 2, 4, 6. No, it's counting by 2.5. Oh my word. This is a terrible graph for me to. Let me grab a different set of axes here. I think I've got it pulled up on my Desmos calculator on mine. I do. Okay, that'll be a little more fitting. All right, let me get this going here. All right. And I just need to see the 16. I'm good there. Sorry, I'm talking to myself, Cyprian. All right, let me put this onto our page. Okay. Make it a little smaller. All right, now we're counting by 1s. Okay. And I see you're typing something, Cyprian. I'm just going to wait to see what you have to say before I go forward. Okay, I see okay, there you are. You're typing again. Okay, I'm looking at the next function in relation with that current one. Okay, that's what we're about to do is put it all onto the same graph here so you can have them next to each other to compare. I'm not sure if that's what you're saying, Cyprian, but I'm going to go ahead with this. Okay. All right, so 0, 0, 1, 1, 4, 2, so we're getting that square root curve, 9, 3, 1, 2, 3 right here, and 16, 4. Okay, so this is what that parent or that toolbox square root function looks like before it's transformed. Now, I will do our transformed function in blue. So this is for g of x equals, okay, so it says add 2 on the inside of the function. So this is the square root of x plus 2, which I'll go ahead and rewrite as the square root of x minus negative 2, because that's how our input is going to change. It's going to change negative 2, so I'm going to subtract 2 from all of my input values. Okay, so I'm going to go ahead and construct my, And so what this says is the only thing that changes about this function are its input values. So now I have an x, g of x chart. Nothing changes about my outputs. 0, 1, 2, 3, 4. And I start with my input values of 0, 1, 4, 9, and 16. And from each of those, I subtract 2. and I end up with my new input values of -2, -1, 2, 7, and 14. And let me just prove to you that you get the same output values. So if I do, let's say, G of 14, that's the same thing as 14 plus 2, the square root of that, square root of 16, which is 4. You get the same output values. The only thing that's changed is your input. So I'm going to go ahead and put that onto the graph. -2, 0. So notice I've shifted left 2 positions, 2 units. -1, 1, 2, 2, 7, 3, and 14, 4. Same exact shape, just shifted to the left 2. How is that for you, Cyprian? It's on the inside of the function where the translation is happening, so that happens on the input value. Oh, and we got to tell what that is. So this is a horizontal shift. Just write this while you're typing. Horizontal shift. And it shifted left 2 units. And for those of you watching the video, Cyprian's typing, so I'm just waiting to see what he has to say. And he says, okay, great. Okay, so combining horizontal and vertical shifts in one function. All right, so notice, let me color code this as well. My vertical shift, this is the one that happens on the outside to the output. So I'm shifting up 4, and then I have my horizontal shift. I have to remember this is happening on the inside input inverse. Would be kind of the opposite of what I would think to happen actually happens. So it says -2, but remember that minus is in the form. So actually what's happening is I'm shifting right 2. I'm going to add 2 to all those input values. And then I have my parent or my toolbox function of the absolute value of x. So let's go ahead and get a picture of the absolute value of x. Oh, before I do that, let me go ahead and grab my better graph. I don't need to see as much with this one, so I can zoom in a little bit, make this a little easier to work with. Okay. Ah, can't grab the corner to make it smaller. There we go. Oh, and I didn't even consider the shifting. Let me grab a better graph. I was just thinking about where we were starting. Okay. Apologize for the delay here. I want to see about this much. Okay. All right. So my parent or my toolbox function is the absolute value of x. So I'm going to start with that f of x table. So this is f of x is the absolute value of x. Of x and f of x. We'll start out with negative, let's do -4 just to spread this out a little bit, -2, 0, 2, and 4. The absolute value of -4 is +4. The absolute value of -2 is 2. The absolute value of 0 is 0. Absolute value of 2 is 2. Absolute value of 4 is 4. So I'm going to go ahead and put my parent onto the graph here. Okay, so -4, 4. -2, 2. 0, 0. 2, 2. 4, 4. A big V. I mean, this is literally like two lines meeting at a point, which is different from the parabola. The parabola is a curve, smooth curve. This is a hard V. So there's my toolbox function. Now, for my new, I have h of x is equal to my toolbox function f of x minus, and I'm shifting 2 in the horizontal direction and 4 in the vertical direction, so up 4. So on my input values, I need to add 2, and on my output values, I need to add 4. All right, so here's my x and my h of x, my new points. Okay, so 1, 2, 3, 4, 5. I started with -4, -2, 0, 2, and 4. And I also started with 4, 2, 0, 2, 4. On my input values, they need to be shifted right 2, right 2, right 2, right 2, and right 2, which gives me new input values of -2, 0, 2, 4, and 6. My output values need to be shifted up 4, up 4, up 4, up 4, up 4, for my new output values of 8, 6, 4, 6, 8. So here are my new points. -2, 8. 0, 6. I'm sorry. Yeah, 0, 6. 2, 4. 4, 6. And 6, 8. So still that hard V, same shape. I have simply moved to the right. Let me get my colors here. I have moved to the right 2 and I've moved or translated up 4 to get to my new function. Was that helpful for you to see those transformations happening simultaneously in the same graph like that, Cyprian? You have any questions about this? And I'm sorry to inform you that we are almost an hour into lecture and we're not quite halfway through the slides. Oh. What I may do, since let me just check the next slide. Let's see. Okay. Write a formula. Okay, so these are translations as well. Let's do this slide, and then I'll ask you to exit the room, and I'm going to exit the room as well so that it cuts the video off, and I'll break this video up into 2 pieces. If you want to come back in and finish the last half with me, feel free, Cyprian, but if you're spent and just want to watch the video later, that's fine as well. Let's go ahead and do this last slide that has to do with translations, and then we'll do this particular section in 2 parts. Does that sound like a plan to you? You can just give me a green check or a red X, or you can type. I see you're typing. All right, cool. Okay. You should know from your toolkit functions that this shape right here is the shape of the square root of x. That's solely gotten from knowing those toolkit functions. The square root of x actually has these points, 0, 0, 1, 1, 4, 2. So this is a picture of the toolkit function, and they're asking us to write the equation for the transformed function. So notice, we have gone to the right 1 unit, and we have moved up 2 units. All right, so I'm going to start by just writing my shell before I actually put my translations in there. So h of x is equal to the square root of x minus. Okay, so we went to the right 1. That happens, the horizontal shifting happens on the input. So I put a positive 1 for h there. And then I went up 2, which is on the outside of the function because it's the output. I went up 2. Did I say 2 or 1? I went right 1 and up 2. That's it. That's all you have to do for this one is just write what that new function is, judging from the graph. So you have to know your toolkit functions to be able to do these, because you have to know that that very first graph that was on the page was in the shape of a square root function. Okay, write a formula for a transformation of the toolkit reciprocal function 1 over x that shifts the function's graph 1 unit right and 1 unit up. I'm actually going to erase that orange there and color code this as well. So I'm doing my horizontals in blue, 1 unit to the right. Well, that's the same as that one. And 1 unit up, okay? So I start out with f of x being 1 over x, and my new h of x, it's got to have that same structure, and I'm subtracting always, so I'm moving 1 unit to the right and 1 unit up. Okay, so that's all I have for you on shifting, so horizontal and vertical shifting. Cyprian, I'm going to go ahead and stop the recording. We both have to log out for about 30 seconds to a minute for it to finalize that video and cut it off. So if you'll come back into the room in a minute or so, if you would like, we'll get going on the next half, which has to do with reflections and stretching and compressing these things. So actually distorting the shape. Let me ask before we leave, are you going to come back? Just so I don't have to wait on you if you don't plan on coming back. It's okay if you're spent. Please don't think I'm trying to lure you back in.